Hello students, in this session we will do the second theory part of motion in a straight line. Got it? In the last session we did complete the difference between distance and then the displacement. We saw that one, and then we saw the intuition and logic behind differentiation integration. Okay, so those were the things that we completed in the last session. In this session we will do the leftover things. Okay, so with this session the theory part of motion in a straight line will get completed. Got it? So the things that we are about to see in this session are like velocity and then the acceleration. Got it? So velocity, in that thing we will see like instantaneous velocity. Fine. So instantaneous velocity is something, it will be the direct application of the differentiation that we have learned. Okay, we'll do that one. Then we will see the graphical relation between differentiation, like the graphical relation between displacement, acceleration and velocity, right? So we'll do that part. Then what we will do is like kinematic equation, those three equations that I've told you, right? So we'll see the proof behind those three equations, v equals u plus at, and those equations. Got it? So the last part that we will do is like the relative motion. With that the theory will get completed, and then you have some extra things into it, right? So we will see which is like local maximum and then the local minimum, right? Some basic max concept that you need to know, right, in order to do the sums. We will see that thing, right? That is like a small section, okay, which will take around 5 minutes to complete. So we'll do that one also, right? So these are the theory parts that we will complete in this session, right? Okay, so with that, motion is straight line, all those concepts will get completed. Next we can directly jump into PYQ. Okay, so now we can see what is meant by velocity. So here you have like velocity. So in order to get the velocity, what I will do, I'll just put change in displacement in the numerator divided by the time interval, right? So change in displacement, that term is actually in vector quantity, right? So velocity should also be in vector quantity. Therefore, velocity is something that plays a predominant role in the chapters that are about to come. Okay, so physics comes with vectors, therefore velocity should play the role, right? Okay, so in order to get velocity, what I will do is I'll have like change in displacement, which is like del x in the numerator divided by the time interval, which will be like del t, right? So this will give me the velocity. Okay, this is like a normal velocity calculation. Then if I need to get the instantaneous velocity, then what should I do? If I need to get the instantaneous velocity, then I'll have to take the change in displacement so small such that the succeeding point and the preceding point should be the same point, right? So I'll have to consider the interval so close. If I need to consider such a close interval, then obviously I'll have to do the differentiation, right? So that is the logic. That's the reason why we study differentiation, and this differentiation comes along the complete physics. Okay, fine. So if I need to get the differentiation, I should take the interval so close. So here how I should consider is, in the numerator you will have dx. Okay, dx. So instead of del x, I'll substitute dx. Same way, instead of del t, I'll substitute dt. Got it? So in order to get a clear understanding of this dx by dt, I have given you a graph here. So in this graph, how I have plotted actually is, I put x in the y-axis, which means displacement is along the y-axis. So the numerator thing is along the y-axis, right? So whenever you do differentiation, I just put dy divided by dx. That is how I learned, right, in majority of the situation. Okay, that shouldn't be an idealized stuff, but dy by dx is something that I put. Y is like an y-axis, therefore in this y-axis I have put x, obviously. Then what should be in the numerator? In the denominator it should actually be t, right? Instead of dx, I'll put like dt. Got it? That is what I have written here, dx divided by dt, right? So now you should know how I have put the graphs. Now what I'm about to do is, I'm just going to find the instantaneous velocity, right? So in this situation, this is obviously a non-uniform motion of that object, right? It should, if it was an uniform motion, it should actually be a straight line, the thing that we have seen in the last class. But in this situation, this is obviously a non-uniform motion. Okay, so non-uniform motion actually means the velocities keep on changing. So that is how it is going to be. So here when I look at the graph, it is pretty clear that the distance is not changing in a linear fashion, it is following some other pattern, right? In this situation, let's see how the pattern actually looks. So it seems to be pretty clear. For 2, it gives me the x to be 4, and then same way for 3, it gives me like 9, right? So it increases in the fashion of square, right? Therefore, if I need to get an equation for this one, then how should the equation actually be? It should be something like this. If it was like y and x, then it should be like y equals x square, because this is increasing in quadratic fashion. But here along the x, it is like t, and then along the y, it is like x. Therefore the equation that I should actually get is x, which is equal to t square. So this is the equation that I'll get, right? Okay, if I need to get an instantaneous velocity, what I will do, I'll have to differentiate it, right? If I differentiate this equation, so I'll have like v, which is equal to dx divided by dt, right? Instead of x, what I'll be able to substitute is like t square, right? So instead of x, I'll be able to substitute the t square. So if I'm about to differentiate this one, it's like x power n, which is equal to nx power n minus 1, right? The formula that we have seen in the last class. Okay, so it should be like 2t power 2 minus 1, which is like 1. Therefore, if I do the differentiation, I'll get the answer to be like 2t. Got it? So this will give me the instantaneous velocity at every single point. Okay, so I'll give you an idea of what is meant by instantaneous velocity. Let's say, for example, you are riding a motorcycle. Okay, so when you are riding the motorcycle, let's say for example, initially the reading on the speedometer was like 40 kilometer per hour. Okay, which means you will be able to cover 40 kilometer in 1 hour, right? So that's the logic. Fine. So for example, then what you do is you just throttle the accelerator. Okay, so when you throttle the accelerator, what happens? The speedometer reading, it increases from 40 kilometer per hour to 60 kilometer per hour. Okay, so the final velocity that you are about to reach is like 60 kilometer per hour. Got it? So as you are increasing the throttle, obviously the velocity is going to increase, right? So this is something like an initial and then the final velocity. If I need to get the velocity at every instant, what I should do, then I just take a clock and then I just find the velocity of the velocity from the speedometer for that particular time, right? For example, if it was like 45 kilometer per hour after certain interval, then at that instant the velocity of the motorcycle was like 45 kilometer per hour. Okay, so if it was like 50 kilometer per hour in the in between interval, okay, then at that instant the velocity of the bike was like 50 kilometer per hour. So that is instantaneous velocity. Initially it was with some velocity, finally it reached some maximum velocity. So those are like initial and then the final velocity. In between time, at that particular instant, if I need to find the velocity, then what I should do, I'll have to find the change in distance in that small interval divided by the time. So that is going to give me the instantaneous velocity, right? So here, if I need to get an instantaneous velocity for a non-uniform motion, which I could actually relate with an equation, then what I should do, I'll have to do the differentiation to get the velocity, instantaneous velocity out of it, right? So here, I'll give you how to calculate the instantaneous velocity. Let's say, for example, at 2 second, or I mean like when time equals 2 second, right? So at that instant, what is the velocity of that bike? So it should actually be equal to 2 into 2, which means like v instantaneous at 2 second was equal to 4 meter per second, right? So that is what this is going to be. So here v instantaneous should be equal to 4 meter per second. 2 into 2 will be like 4 meter per second. Same way at this point, the v instantaneous should be equal to like 3 square, right? I mean like 3 into 2, 6 meter per second. Got it? Now what I did find is I just found the instantaneous velocity at those two intervals, right? When time t equals 3 seconds, at that point, when time was equal to 3 seconds, the velocity that I got in the bike was like 6 meter per second. Got it? Same way at t equals 2 seconds. At that point, I'm going to freeze the time and then I'm going to look at the speedometer. It showed me like 2 meter per second, 4 meter per second, right? So that is what I've written over here. So these are like instantaneous velocity, fine. So if I need to get the average velocity, which means, let's say this guy is covering from 4 meter to 9 meter with an interval of 1 with an interval of 1 second. Okay, so I'll have to get an average velocity out of it, right? So the average velocity is, if I'm about to move with that particular speed, I'll be able to cover that same amount of distance in the given time, right? But in the situation, actually, as I was giving the throttle, the velocity was changing and then it reached like 6 meter per second. Got it? But here, what should be the average velocity such that if I travel with that same velocity, I'll be able to cover the same distance. Okay, so that is what is meant by average velocity, right? So if I'm about to find the average instantaneous velocity, is easy to find, which means if I do the differentiation, then I'll get the instantaneous velocity. If I'm about to find the average velocity, what I should do, I should consider that total distance covered divided by that given time interval, right? So the distance covered in this situation was like 9, final point minus initial position. So that's going to be like 9 minus 4. Therefore, V average will obviously be like 9 minus 4 divided by the time interval, which is like 3 minus 2. Got it? Therefore, the answer you will get is like 5 meter per second. Fine. As we have expected, 5 meter per second will be like in between of like 6 meter per second and then the 4 meter per second, because this velocities keep on increasing and then it reaches 6 at some point. Okay, but here if I'm going to travel with this 5 meter per second constant velocity, in that situation also I'll be able to cover this distance in that given time. Okay, so that is what is meant by average velocity, right? So you should get to know the idea between average velocity and then the instantaneous velocity. Okay, so instantaneous means I'm just going to freeze the clock at that particular instant and then I measure the reading out of it. Okay, so that gives me the instantaneous velocity. Average velocity means you are going to take some duration and then the velocity keeps on changing in that particular duration. But if the thing is, if I'm about to travel with the same velocity, then what should be the velocity to cover that exact distance in that given time? So that is what is meant by average velocity. Okay, so you should be clear with the notion that I have told you here. Okay, so in order to get instantaneous, do the differentiation. If you need to get the average, just take the whole distance divided by the time, you will get the V average. Okay, fine. So we should be clear with velocity, right? So whenever the term velocity comes into picture, so displacement is something that should come into mind. Okay, even if I tell you like distance, okay, in the upcoming chapters the word distance will come into picture. Still you should be clear, if they have given you the velocity, then obviously it should be displacement, right? So you should know to cross match that one, right? So then comes acceleration. So acceleration actually means how does the velocity change with respect to the time. Fine. So here in the above case, what I did is I just considered change in distance displacement divided by time interval. But in this situation, what I'm about to consider is change in velocity divided by time interval. Okay. The same bike situation. Let's say the speedometer reading changed from 40 km per hour to 260 km per hour, or else we can make it simple from 4 meter per second to 6 meter per second. Okay, in a time interval of 2 seconds, then acceleration should be like final velocity minus initial velocity divided by the time interval, which means like 6 minus 4 divided by 2. Okay, so I'm going to change the velocity in terms of like 1 meter per second at every 1 second interval. Okay, so we'll do this acceleration thing. Okay, while doing graph, we'll get a clear idea out of it. As if now what you need to know is acceleration actually means change in velocity divided by the time interval. Okay, velocity means change in displacement divided by the time interval. Okay, so this is like a next level to the velocity. Okay, so from displacement I'll be able to get the velocity, same way from velocity I'll be able to get the acceleration. Okay, so here acceleration equals change in velocity divided by time interval. Therefore if I'm about to notate it, you'll have like del v divided by del t. Okay, change in velocity divided by the time interval, or else I'll be able to notate it something like this. For instantaneous, it will be like dv divided by dt, right? So here velocity is actually a differentiation of displacement. Therefore, it will look something like this. Okay, these are notation. So d divided by dt of d, instead of velocity, I'll be able to substitute dx divided by dt, right? Okay, first if I gave you like x, then differentiate it once to get the velocity, then differentiate it again to get the acceleration. Okay, so that is what this represents, obviously. So when you differentiate one time with like x, you'll get the velocity. So dv by dt will give you the a instantaneous. Then you do it differentiation one more time, right? Got it? Okay, so either you could write something like this, d by dt of, and inside a bracket you'll have like dx by dt. Okay, or else you'll be able to write in another notation, which is like, this is the common notation that we generally used to write it, which is like d square, okay, divided by dt square, and then you have like x. So generally we tell this one as d square x divided by dt square. Okay, so you should be clear with this acceleration also, right? So now we have done the understanding between velocity and then the acceleration. Same way we did what is meant by instantaneous velocity and then instantaneous acceleration, right? So now we are ready to see the graphical part that gives me the relation between displacement, velocity, and then the acceleration, which is something that we will see in the next page. Okay, now we can see the graph that relates between displacement, velocity, and then the acceleration. Okay, so here the displacement is actually linearly increasing. Okay, so the displacement is linearly increasing in the first case. In the second case, if I see like the displacement is linearly decreasing, which means in the first case x was like 0, it started from 0 and then it increases from 0, it just moved something like this, 1 2 3 4. But in the second case it was like it was decreasing, therefore it should start from like 4 and then it was moving backwards, 4 3 2 1. That's how it moved, right? So here it is like linearly decreasing the displacement. And in the third case it is pretty clear. So x is constant, which means the object is stationary, which means at rest. Okay, so these three are the graph. Now what I should do is I'll have to find for this exact graph how should the velocity actually be and how should the acceleration actually be. That is what I need to find here. Okay. So here in the first situation, if I consider the velocity, I mean the displacement is increasing, right? Therefore, if I put like final point minus the initial point, let's make it this way. The final point is like 4 and then the initial point is like 0. If I put like 4 minus 0, it should actually be positive, right? So the velocity should be positive. That is done. Got it? Then let's see how should the velocity be. It should it be linear or should it be curvy? That is what I need to find. So this is actually a straight line, right? If I need to get a velocity from the displacement, what I do, I just do a differentiation of it, right? So this equation could be like x equals to t. So instead of y, I just put x, and then instead of x, I just put t. Okay, so the equation is something like this: x equals to t. Then if I'm about to differentiate this one, then I obviously get like 2, right? If I'm about to differentiate a linear equation, then the differentiated answer that I get is like a constant. Okay, so it should be clear, right? Therefore, the velocity here is actually positive, that is not. Same way, the velocity should be like constant, which means in this situation, this object is in uniform motion, right? This is something that we have already seen, right? In the last class itself, we did see when x is changing in a linear fashion, then obviously it should be like an uniform motion. The reason why I call it as an uniform motion is because in that situation, the velocity will be like constant. For example, if the velocity was like 4 meter per second, till the end of the journey, the velocity will be the same 4 meter per second, which means the object will cover 4 meters in every 1 second. Okay, so that is how it's going to be. Okay, so for the first case, I did find the answer, which means the velocity was constant and it was like positive. So you had like positive constant velocity. Okay, so if I am about to plot the graph, it should be like plus v naught. Okay, if it was like 4, it is going to be 4, or else it will be like plus v naught. Right, now I have got the velocity for that particular displacement time graph, right? So the next one is like the other way around, right? So it is increasing. In the second case, we are just moving backwards. That too, we are moving backwards with the same constant velocity, right? If it was a linear equation, I have already told you it should be like constant velocity, right? So the one part is already known, which is like this is like constant velocity, which means this is in uniform motion. Then let's see which sign should it be. The sign should be like final velocity, final position minus initial position. That gives me the velocity, right? So final position here is like 3 and the initial position was like 4, right? So 3 minus 4, I'm just giving you a consideration here. So 3 minus 4 will be like minus 1, something like that. Therefore the velocity should be negative. So negative constant velocity should be my answer here. Okay, so now for the second graph, for the second displacement time graph, the velocity and the time graph will be something like this. It should be in the negative axis, y axis. Therefore, we have something like this, negative v naught, right? Now I did find the answer for like first one and then the second one. Then for the third graph, it is pretty obvious. The position of that object didn't change at all. Therefore, it should be at rest. For the third graph, it should be like at rest. Okay, then what should be my velocity? So velocity should obviously be like 0, right? Because the object didn't change its position, right? Therefore the velocity v will be equal to 0. Got it? Now I did find the relation between velocity time graph, right? So the next thing that I'm about to see here is like acceleration. So acceleration should obviously be 0. This is an easy thing, right? So here velocity is not changing at all. This is something like this. This relation, from this relation I got the answer to be 0. So if I differentiate this once, I'll get the acceleration, right? So here velocity was constant, therefore final velocity minus initial velocity will be like same thing, therefore it is 0. If the numerator was 0, then obviously acceleration should also be 0, right? The velocity didn't change at all, then you wouldn't have any acceleration into it, therefore the acceleration here was 0, right? So this relation should be clear. So what, it doesn't matter whether it's moving forward or backward, you get the same negative 4 minus of minus negative 4, again that's going to be 0. Therefore for all those three situations, the acceleration was equal to 0, right? So the idea that you should develop is the acceleration could be 0 when the object was at rest, or else the acceleration could be 0 when the object was moving with a constant velocity, which means when the object was at uniform motion, right? So this is the idea that you need to get from these graphs. Okay, you should be clear with the first set of graphs, then we can move on to the next set of graphs. Okay, so here what actually happens is In the situation, the velocity is increasing. Okay, the velocity is not constant. In the above situation, the velocity was constant, but here the velocity is linearly increasing, which means, let's make it this way, v could be equal to 2t. At the initial, when time t was equal to 0, 2 into 0 will be like 0, velocity was 0. Same way, when time t was equal to 1 second, the velocity will be like 1 meter per second, 2 meter per second. And then when the velocity was, time was equal to 2 seconds, the velocity will be like 4, right? So it is increasing in a linear fashion. Same logic. Here, the velocity is increasing in linear fashion, right? So the acceleration will be related in a quadratic way. So acceleration, I mean, like displacement will be related in a quadratic way. Okay, so we'll do that one. So how will it get related in a quadratic way? That is what kinematic equation comes into picture. As if now you need to know that idea, right? If velocity is linearly increasing, then obviously the displacement should be changing in a quadratic fashion. Okay, so in the previous section, in the previous part where we studied instantaneous velocity, we consider that equation to be like a quadratic equation, displacement time equation. Same notion here also. So here you have like velocity time. So velocity is actually linearly increasing. Then what should happen to the acceleration? Obviously, final point minus initial point. Same way you do the same thing that I have done here. So acceleration should be like positive. Final velocity minus initial velocity will give me a positive value. Therefore, acceleration is like positive, which means constant acceleration. Got it? So here the velocity will be increasing at a constant rate. For example, initially if the velocity was equal to 0 when it started, then after 1 second the velocity could be equal to 2 meter per second. Then it could be like 4 meter per second. Then after 1 second it could be like 6 meter per second. So every 1 second the velocity was increasing at the rate of 2 meter per second. That is what this represents. Okay. So here if I consider the acceleration, acceleration should actually be positive acceleration. Got it? It is like positive constant. Got it? So constant, and then it is also in positive direction. Fine. So then what happens to the velocity? Velocity is actually linearly increasing. Linearly increasing. In which direction the velocity is increasing? It is also increasing in the same positive direction. So velocity is along the positive direction. Got it? Then comes the x. So x, how is it changing? Actually, it is also, the vehicle is also moving in the positive direction. Therefore, x will also be in positive direction. Okay. So now I got the relation between acceleration, velocity, and then the x for a linearly increasing velocity. Okay. Got it? So next we can see if how should it look when it seems to be like linearly decreasing. Okay. Next one is also same velocity time graph as usual. So here what actually happens is velocity is linearly decreasing. Okay. So obviously velocity seems to be linearly decreasing, right? So this situation could be considered like in braking case. Okay. So here what actually happens is the velocity, initially the velocity of that object could be like 4 meter per second. Okay, it was traveling in the plus x direction, the velocity was equal to 4 meter per second. Then what happened is the velocity decreases from 4 meter to 3 meter per second, then it decreased from 3 to 2. Okay, so here the vehicle is getting braked. Okay, so we are just braking the vehicle. Therefore here in this situation the acceleration is obviously negative as usual. The acceleration is negative, which means I am just slowing down the car. Okay, therefore the acceleration is constant and also it is negative. Okay, the first one is done. In the second situation, what will happen to the velocity is velocity is linearly decreasing, but still the velocity is positive, which means you got like plus 4 meter per second, then you got like plus 3 meter per second. The car didn't move backwards, the car is slowing down. Therefore the direction of the velocity is still in the positive direction. Okay, then what should happen to the x? The x should obviously be in the forward direction, right? Even though I'm just slowing down the car, still the car is moving in the positive direction. Therefore the direction of the x should also be in positive direction. Got it? So if I write it down, then you'll have like, for acceleration this is like constant, but it will be in negative direction, which means the car is slowing down. Final velocity, if I do like final velocity minus initial velocity, then obviously final is less when compared to the initial, therefore it will be negative. Okay, so whenever you have an acceleration with negative, it actually means the car is braking. Okay, or else the car is moving in reverse direction, which we'll see next. As if now it could be like braking condition. Okay, then for the velocity, how should it be? It is like linearly decreasing, right? Velocity is linearly decreasing, or else it could be like, it is like linearly decreasing. and then same way the velocity is in positive direction, right? I could call this situation as a braking case. The car is moving forward still, but yet the car is slowing down. Okay, so the next one is like for x, it is obviously in the positive direction, which means the car is still moving in the positive direction, but it is getting slowing down. Okay, therefore this is still in the positive direction. Okay, so then you have this term. So this is like velocity was linearly decreasing, but still this was in the first quadrant. Okay, but here the velocity is in the fourth quadrant. Okay, so how should it be when it is in the fourth quadrant? When it is in the fourth quadrant, actually acceleration is still constant, but it is negative. Got it? Constant, but it should be like negative, because final, when I do like final minus initial, final point, let's make it this way, -4. The initial point was like -3 meter per second. So -4 minus of -3, which is like -4 plus 3. Got it? When I do the final minus initial, the initial part negative and negative becomes positive, therefore you will get like -1 meter per second square. Got it? Therefore acceleration is constant, that too it is negative, right? So when acceleration is constant and negative, you got like two conditions. One is for like braking, the other should be like when the car is moving backwards, right? So here if I consider, it is like minus v naught, therefore when it is like negative v naught, obviously it should be like -3 meter per second, then it could be like -4 meter per second, and then it keeps on increasing in the negative, then comes -5 and all those things, right? So here the car is increasing in its speed in the reverse direction. Okay, so the velocity here should be like linearly. Okay, the velocity is increasing, the value of the velocity, it is increasing from -4 to -5, -6 and those things. Therefore the magnitude is actually linearly increasing. In which direction? It is increasing in the negative direction. Okay, got it? So velocity is actually, the value of the velocity is actually increasing, but the point is it is increasing in the negative direction. Okay, so then comes direction of the x. So the direction of the x should obviously be negative, right? Because I'm just covering it in the negative direction, right? Final minus initial, if I put like del x, final minus initial should obviously be in the negative direction, which means the vehicle in itself is started moving backwards. In the first case, vehicle was slowing down, then after getting slowed down to rest, then it started moving backwards with an increase in velocity. That is what this represents. Therefore x should be in negative direction, linearly increasing, which is negative, then x should be in negative direction. Got it? Now I have got all those things into picture. So next what I'm about to do is I'll just consider this complete graph into a single, I'll consider the entire graph into a single graph. Okay, now this graph is actually a combination of last two graphs that we have seen. So here you have velocity that is slowing down, which means the vehicle is slowing down, and then at time t1 the velocity becomes 0, then velocity starts increasing in the negative direction. Okay, so this is pretty clear. The slope of the velocity is actually negative, therefore acceleration at all those instants should be negative, right? So acceleration here is like constant. Okay, you shouldn't have any doubt on this graph, because this is actually a combination of those two separate graphs that we have seen, right? Therefore acceleration should be constant, that too this will be in negative direction. Okay, so the first one is done. Then what we are about to do is we will see the velocity for the interval between 0 to time t1. Okay, then same way between the interval t1 to t2 we will see the velocity. Okay, so for like 0 to time t1 the velocity will be like linearly decreasing. Got it? Right? Therefore the velocity should be linearly decreasing, which means the value of the velocity is decreasing, magnitude is decreasing from 4 meter per second goes to 3, 2 and then, which means this situation is like a braking situation. Still the velocity is in positive direction, therefore the velocity is going to be like positive. Okay, from t1 to t2 what actually happens is it just stops and then it started moving backwards with increasing velocity. Okay, therefore it should be like linearly increasing, but the velocity is negative. Okay, it should be like linearly increasing, but the velocity is actually negative. Okay, got it? So the same statement that I'm writing here also, but the thing is I have just combined those two graphs, that's it. Okay, so what should happen with respect to the displacement? So in the first situation the car was still moving in the positive direction. Okay, therefore for 0 to t1 the displacement should actually be in positive direction. Okay, and then after moving in the positive direction, then it stopped and then it started moving in the reverse direction. Okay, so in the first situation, still it just covered for 3 to 4. That's how it moved like 3 to 4, 4 to 5. That's how it moved. Then from T1 to T2, it started moving backwards. If it was like backwards, it should be like 5 to 4, 4 to 3, right? If I put like final minus initial, then I'll get the value displacement to be in negative. Okay, therefore for T1 to T2, the direction should be like negative direction, which means the vehicle started moving the other way around. In this situation, it could be like minus x. Okay, therefore the direction here is negative direction. Okay, you shouldn't have doubt into it. This is just the combination of those two graphs that we have already seen. Okay, that we have seen prior to it. Therefore these two graphs just combines and then it gives me this third graph. Got it? You shouldn't have any doubt in this part. It should be like clear. Okay, first we saw like if the displacement was linearly increasing, then how should the velocity be, right? So the second pattern that we saw was like if the velocity was linearly increasing, then how should be the acceleration to it. Okay, the third category of graph that we are about to see is between x and then the time. Okay, so here x is along the y-axis, which means displacement is along the y-axis. Okay, so here you have like a curvy one, right? So it could be like the equation could be something like this: x equals t square will also give you a curvy graph, or else it could be like x equals t square t square plus 2t cube or some other relation. Okay, so if the power was more than 1, then you will get a graph that should look like a curvy one, right? So depending on the powers, you will get the steepness of the curve changes. Okay, so here you have displacement time graph where the graph looks like a curvy one, right? Okay, so what actually happens here is how should the acceleration be? That is something that I need to get. So here I have directly given you it should obviously be positive. Anyway, in order to get this understanding, first I'll have to determine the velocity. Okay, so here the velocity is facing downwards, then it becomes 0, then actually it is increasing. Okay, so what actually happening here is in the first situation, let's make it this way: the velocity was equal to minus 4 meter per second. Okay, then here the velocity could be equal to 0, then in between obviously it should be in between those things, which means like minus 3 meter per second. Fine, so here it seems to be pretty clear. The velocity is actually decreasing to 0, right? So here the velocity, the magnitude of the velocity, I'm just telling you, not the direction. Don't consider that negative sign. I'm just telling you the magnitude. So the velocity is just decreasing and then it goes to 0, then velocity starts increasing. Okay, here what actually happens is the direction of the car is actually changing. Okay, of the vehicle is actually changing. So here if I consider the first part, it seems to be like car is slowing down in the negative direction. Okay, so initially the car was moving backwards with a velocity of minus 4 meter per second, and what actually happens is it is going in a reverse direction. Okay, so the velocity started decreasing and then it reached 0, then it started moving forward, right? So that's how it should be related. Obviously minus 4 minus 3 and then it goes to 0. From 0 it started increasing, right? So 0 1 2 3 4. So the velocity, the car started moving backwards. Okay, which means when it was moving backwards it has more velocity, then the velocity started decreasing, which means the car started slowing down in the reverse direction, then it just moves forward with an increasing velocity. So that's how it should be related, right? So for the first case it should be like car slows down, okay, in negative direction. Okay, then what should happen to it? Then car started moving forward, speeds up in positive direction. Okay, so car speeds up in positive direction. Okay, now let's consider the acceleration into it. If I consider the acceleration for the first half, it should be like here the velocity was like minus 3 and here the velocity was like minus 4, minus 3 minus of minus 4. Therefore, this becomes positive, right? Minus 3 minus of minus 4. Also, we'll get something like this: minus 3 minus of minus 4, right? Therefore this term will dominate. You will have the acceleration to be positive, right? So change in velocity gets you the acceleration. Therefore when the curve is like open upwards, you'll get an acceleration to be positive, right? Obviously this is pretty clear. Final velocity is much greater than the initial velocity, therefore the acceleration of the later second half should also be positive, right? So in this situation, for the first case acceleration was positive, which means the car was moving the car was actually slowing down in the negative direction, then it started moving forward with increase in velocity along the positive direction. Okay, so that's the first graph that you need to know. So the next graph is exactly opposite to that of the first graph. So in this situation, obviously this is like other way around, therefore acceleration should be negative. Got it? So what is actually happening here? Here the x was increasing, right? And then it started moving backward. So in the initial situation, if I consider the x was like in the positive direction, velocity is actually in the positive direction, then it goes to 0, which means if the velocity here was like 4 meter per second, then at this point the velocity is obviously 0. Then in between point it should be like 3 2 1 and then it goes to 0. So here the car was moving forward, the car actually slows down in positive direction and then it speeds up in the negative direction. This is like exactly opposite to that of the graph that we have seen above. Therefore here you should have something like this. Car slows down in positive direction, slows down in positive direction. Okay, it should be clear. Then what happens to it? Then the car starts moving backwards with increase in velocity. Okay, so car speeds up in negative direction. Car speeds up in negative direction. Okay, acceleration should obviously be negative because this is like opposite to that of the above condition. If I put like final velocity minus initial velocity, final velocity is obviously less when compared to the initial velocity, right? So if I put like final minus initial, obviously the numerator is going to be negative. Therefore acceleration in this situation has to be negative. Okay, so if they have given you the displacement time graph and then if they are about to ask you to find the acceleration, if it was like open upwards, then the acceleration should be positive. Okay, if it was like open downwards, then the acceleration should be like negative. Okay, you should be clear with this one. Then before going into kinematic equation, there is this one part which you need to know. So area under velocity time graph. Okay, so if they are given you area under the velocity time graph, what should this actually signify? Okay, so here as I'm measuring area, I'll use integration. Okay, so what is the equation for like velo what is the equation for the velocity? Velocity should be equal to dx divided by dt, right? Got it? So velocity should be equal to dx divided by dt. Now what I'm about to do is I'm just going to do the integration for the displacement. Okay, so if I do the integration, what should I get? Dx will be equal to v dt, and then I do the integration. So if I do the integration, what should I actually get is, you will have a relation, you'll get a relation between x and then the v dt, right? So here if I do the integration, I'll get the displacement, right? So displacement will be equal to the integration between v dt, v and then the t. Okay, so whenever I do the integration, what I actually do is I actually find the area under that particular graph. Okay, this is something that we have seen exhaustively in the last class itself. So whenever you do the integration, you are just finding the area under that graph. So when I get the area under the graph and then I plotted, those areas will get plotted, right? So here if I am about to do integration between velocity and then the time, velocity and then the time, what will be the integrated answer? So the integrated answer is nothing but the left hand side here, which is going to be the displacement. Okay, so whenever you do the integration between velocity and then the time, which means whenever you calculate the area under the graph between velocity and then the time, you actually get the displacement covered. That is what you get. Okay, so here displacement covered, if you do the integration, you get the x, which is nothing but integral of v dt. Okay, so here the graph, area under the graph actually represents displacement covered. Okay, you shouldn't have any doubt into it. Fine, it should be clear. So here I did find the area under the graph between velocity and then the time. So when I got the area under the graph, it was supposed to be equal to that of the displacement covered, because here area under the graph actually signifies the integration that I'm doing here. Okay, so you shouldn't have any doubt in this part. Next we will see like kinematic equation. Now we will see kinematic equation, right? So kinematic equation for uniformly accelerated motion. So uniformly accelerated motion actually means the acceleration is constant. Okay, so I have used the same wordings as if it is in the NCRT. Okay, so when you get like uniformly accelerated motion means the acceleration is actually constant. Okay, so that is what this represents. We will do this one, right? So for an uniformly accelerated motion, what we could consider is dropping a ball, right? So on the earth surface, we know from the lower grades, acceleration due to gravity is going to be constant closer to the earth's surface, which will be equal to 9.8 meter per second. Got it? Acceleration is constant, right? If the acceleration is constant, then from the graph we actually know velocity should be linearly increasing. Okay, so here you take a ball, right? So for uniformly accelerated motion, I'll consider a ball that is being dropped from certain height h with the surface of the earth. Okay, so here in this situation, I'll not consider the air resistance, because when you drop a ball, obviously you'll have an opposingly you'll have an force which is acting because of the air resistance. We wouldn't consider that air resistance in the situation, which means that the area is completely vacuum, and then you're going to drop a ball, right? So it doesn't matter, mass doesn't come into picture. So it doesn't matter whether you drop a coin or a feather. We know that experiment, right? Feather and coin experiment. If it is in perfect vacuum, then obviously both those things will reach the ground at the same time, because acceleration due to gravity g is going to be constant. Okay, so here I'll consider the acceleration to be a itself. If needed, I'll substitute it with g. Okay, so g is nothing but acceleration due to gravity with respect to the earth. I'm just talking about it. Okay, so here I'm going to drop a ball, which means I didn't give any initial velocity to it. I just dropped it. Okay, I didn't throw it downwards, I just dropped it. Therefore you are going to have initial velocity u to be equal to 0, right? So then what happens is, after 1 second, obviously the acceleration here is going to be like 9.8. Okay, so acceleration here will be like 9.8 meter per second square, right? So this is in negative direction, because here the ball is falling downwards. So generally plus y means something that is moving from the earth's surface, negative means it is moving towards the earth. Okay, therefore I'll put the sign convention itself into it. You'll have like minus 9.8 meter per second square, right? So what happens to it after 1 second? The velocity of the ball will reach something like this, minus 9.8 meter per second. Got it? So initially the velocity was equal to 0, and then the velocity got increased to minus 9.8 meter per second, 9.8 meter per second when time was equal to 1. Then what happened is, then when time was equal to 2 seconds, the velocity got increased to another one, 9.8 extra to it. Therefore you'll have like 9.8 plus 9.8, you'll have like minus 19.6. Okay, minus 19.6 meter per second, right? So in the situation, the velocity increased from 0 to negative 9.8. So the distance covered will be less. In the next interval, obviously this is increasing from minus 9.8 to minus 19.6. Therefore the distance will be much more greater to it, right? So in order to calculate this distance, we'll get a kinematic equation out of it. From that we'll be able to calculate this distance. Okay, got it? Fine. So then what should be the velocity at time t equals 3 seconds? You'll have to add extra one 9.8 to it. So you'll have something like this, minus 29.4. You'll have like minus 29.4 meter per second. Okay, so I know the value straight away, therefore I did write it down. So if you just keep on adding it, 9.8, 9.8, 9.8, you'll have like minus 29.4, right? So this is how it is going to increase. Fine. So velocity is actually linearly increasing, which means acceleration in this situation is constant. Okay, so here what I'm about to do is, I'm just going to find those three kinematic equations. So in order to get those three kinematic equations, the logic that I'm about to use here is like area under the graph. That's the trick that I'm going to use here. So if I'm about to use area under the graph, obviously the graph that I'm about to choose is like velocity time graph. Okay, so here I did choose velocity and then the time graph. Okay, so velocity will be along the y-axis and the time will be along the x-axis. Okay, so area under this graph will give me the displacement covered, right? So with this displacement, I'll be able to get what will be the distance covered in between t equals 1 to t equals 2 seconds. I'll be able to get that one. As if now, in order to plot the values into the graph, what I'm about to consider is, when I drop from certain height, the initial velocity was 0. Okay, so that was a convenient, easy situation. But that shouldn't be the case every time, right? So I should get a generalized equation. So in order to get that generalized equation, let me consider that I'm just throwing down the ball with some initial velocity. Okay, so when I'm about to throw this ball with some initial velocity, I'll call that initial velocity to be like u. Okay, so the initial velocity was like u, and then what should be my final velocity? Final velocity is like v. Okay, so this is the general convention that we will stick to. Okay, till the end of the physics, we'll consider this to be the convention. Initial velocity is like u, and then the final velocity is like v. Okay, got it, right? So now what I need to find is, I'll have to find the acceleration, right? So if I have to get the acceleration, what should I do? The thing is like, acceleration a should be equal to, acceleration a will be equal to final velocity minus initial velocity divided by the time interval, right? So A equals V minus U by T, right? If I just rearrange this one, I'll get the first kinematic equation, right? So if I do the rearrangement thing, I'll have something like this: V equals U plus AT, right? Straight away, you got the first kinematic equation, which is going to be like, you do the cross multiplication, you'll have, you do the cross multiplication and then just flip the sides of the U, right? So you'll have V equals U plus AT, right? It should be clear. AT and then minus U becomes plus U. Therefore, you have like U plus AT, and on the left hand side, you obviously have like V. Okay, so this will be my first kinematic equation. So the first equation is done. Okay, so the next equation is something related to the displacement. Okay, so if I have to get the displacement here, what I should do? I should be able to calculate the area under this graph, right? If I am able to calculate the area under the graph, then obviously I'll be able to get the second equation, which will be related to the displacement. Okay, so in the first equation, the relation will be such that it is related between velocity and then the time. Okay, so the next relation will be the relation between displacement and then the time. Okay, so here you have, in order to get the area under the graph, you have like one rectangle or square, it depends. You have one rectangle and then the one triangle. Okay, so as far as rectangle is concerned, it is pretty easy, right? So the initial time was like 0 and then the final time was like t. Okay, 0 to t. So that gives me the length, and then in order to get the breadth in this situation or the height in this situation, that's going to be like u. Okay, so that will give me the area of this rectangle or triangle. Then I'll have to get the area of this rectangle or square. So in order to get the area of this triangle, what I should do? I'll have to put half into base into height. Base is not a problem. That's going to be like t. What should be the height? So in order to get the height, it's like final v, final point is like v, initial point is like u. Therefore, this distance should be equal to v minus u, right? So now I have got that in between gap, which will be equal to v minus u. So that part is done, right? Okay, so now I'm ready to get the area under the graph. So the area under the graph here should actually be equal to displacement, right? I'll represent displacement by S. Okay, so that too is a notation that you need to remember. So in order to get that notation, what I do is like S equals, what should be the area for this first part? It should be something like this, which is U into T, right? So the first thing is done. So this will be like the first part, which is like U into T. Okay, so the next part that is going to be plus half into V minus U, right? So V minus U should be the height in the situation, and the base is going to be the same T, right? So you'll have something like this, UV minus U. Okay, so you'll get like V minus U, and then you'll have like T, right? So this thing doesn't seems to be fancier, right? So you have an equation over there. In this complete relation, you don't have acceleration into it, you just have final velocity. So in order to put the acceleration into it, and then I'll have to get rid of this velocity, final velocity, what I do is V minus U should be equal to A times T, right? Cross multiplication seems to be the best possible way. Therefore, instead of V minus U, I'll substitute AT, right? So when I do the substitution, you'll get the final equation, right? You'll get the final equation straight away. S equals ut plus half, you'll have like at and then multiplied by one more t, so it will give you like at square. Okay, so now I am done with the second kinematic equation. So second kinematic equation actually relates between the displacement and then the time. Okay, so you'll get a relation between the displacement and then the time. Obviously that thing is done. Then what I need to find is, I'll have to find the third kinematic equation, which relates between displacement S and then the velocity. Okay, so velocity time is done. Same way, displacement time is done, and then the only thing that is missing is velocity and then the displacement. Okay, so in order to get that one, what I do is I'll have to find an average velocity. Okay, so here this is like a linear line, right? So linearly increasing line. So in order to get an average velocity for it, what I'm about to do here is I'll have to find the average velocity, right? If I consider square or a rectangle, okay, now I'm about to cut it into two equal halves. If I need to cut it into two equal halves, either I could cut it horizontally or I could cut it diagonally. Both those things will give me the same equal area up and down, right? So here if I consider this above rectangle, here in this situation it is cut diagonally. Okay, so this area and this area is the same, or else how I would be able to cut, I would be able to cut it horizontally, okay? So this, when I cut it horizontally, the velocity is going to be constant, right? So that will be my average velocity, right? So here, what I'm about to do is I'm just going to cut this one horizontally. I'll explain it in a bit, in a minute, okay? You'll get it. So this is like V average, okay? The reason why I took this one to be exact center to be my V average is because, so this area and same way this area, both is the same thing, right? So you take a rectangle and then split it into two halves. Either you could split this way, these two areas should be same, or else you could split in between, right? So those horizontal, those two flat areas should also be same, right? So V average should be the midpoint of this section, right? So now I need to find variable relation between V average using V and then U, right? So to get that one, V average will be equal to, so average velocity is this midpoint, right? So if I need to get this midpoint, what I should do, I'll have to consider this u initially, right? So this is the midpoint that I need to get, so this will be like u. Got it? So I put u into it, so you have u, and the next part will be this section, right? So that will give me this V average. Fine. So here what I'm finding is like, what is the distance of this Y from 0? That's what I'm about to find here. So initially this distance is going to be like u, so this part is missing, right? So in order to get this part, what I should do, V minus u gives me the entire section, so I just need half of it, because this is obviously going to be a midpoint, right? Therefore you'll have like u plus, you'll have one more u, and then V minus u divided by 2, right? So V minus u will give me the entire section, that is not needed, only half is needed in order to get that midpoint. Therefore it should be like V minus u divided by 2. Okay, now you do the cross multiplication and do the math, you will get the answer straight away. So you'll have like something like this, 2u plus V minus u divided by 2. Okay, so the answer that you will be left with is V average, which is equal to u plus V divided by 2. Okay, so now I have got this V average. I'm ready to find the third equation. Okay, so third kinematic equation could be found using that V average, right? So the thing that I found above was like V average, okay, which was equal to V plus U divided by 2. Okay, this is something that I found. So generally, what is velocity? Velocity is nothing but displacement covered divided by time, right? So I'll put that notation. Initially it started from 0, so S divided by time, also initial starting time was like 0. Okay, so instead of putting del S divided by del T, I just put it straight away, S by T. Okay, it should be clear. So now I have done like V average equals the distance covered, right? So this distance and this distance is the same thing. Now I have found an average velocity. So here the idea is, if I'm about to move such that the increasing velocity was in this fashion, or else I could also move with a constant average velocity, which should be equal to v plus u by 2, right? So both those situations, I'll end up covering the same distance, yes, right? So here it was because of the increase in velocity, you end up covering the same distance or displacement, which is going to be like s. Same way, while using like v average, I too ended up covering the same displacement, given that the velocity was constant, that was equal to the average velocity. Okay, so it should be clear. Now what I'm about to do is I'm just going to do the cross multiplication. Okay, I just consider the second part of the equation and I do the cross multiplication with time. Okay, so when I do it, I'll have something like this. You end up getting s equals v plus u divided by 2. The first part is done. Then instead of time t, so let's make it this way. So instead of time t, I just use the first equation. So you do the cross multiplication, you get like t equals v minus u divided by a. I'll substitute that one. Okay. So the second part is something like this, v minus u divided by a. So instead of t, I substitute v minus u divided by a. Okay. So this one seems to be relatable, which is like v plus u, b minus u. Okay, so a plus b into a minus b, that's going to be like v square minus u square. Therefore I'll just change this term as v square minus u square. Okay, so if I change that one to v square minus u square, I'll get the final third kinematic equation, which is like v square minus u square, that is equal to the denominator, it goes to the numerator, and you get like something like this, 2as. Okay, so this is the third kinematic equation that you need to know, right? So now I have found three kinematic equation. So if you need to use this three kinematic equation, one thing is mandatory, which means acceleration should be constant. Only when you have constant acceleration, you will be able to use these three kinematic equation, right? So these three kinematic equation will use in like multiple things. Okay, so in upcoming chapters, in multiple chapters, you'll use this kinematic equation, so you'll have to be clear with this equation. Okay, so this equation is actually a foundation. We will use this chapter in the 12th standard, which in electrostatics, and then we will use it in like fluid mechanics and all those rest other chapters. We will use this three kinematic equation. Okay, so the equations are v equals u plus at. Same way, the next one is like s equals ut plus half at square, and the third one is like v square minus u square equals 2as. Right, these three kinematic equation will be valid only when you have constant acceleration, or else it won't work out. Okay, so you should be clear with this kinematic equation. Next we will see like distance covered in the nth second. Next one is distance traveled in the nth second. Okay, so I'll tell you what is meant by nth second. Let's say for example you are dropping a ball with initial velocity u. It could be 0, it depends. Okay, in this situation the initial velocity was equal to u, right? So I'm just dropping it down such that it could have covered some distance when time t equals 2 seconds. Okay, same way it could have covered some distance when time equals 3 seconds. Okay, so if I'm asking you to find distance traveled in the third second, okay, if I'm asking you to get what is the distance traveled in the third second, which means in this interval, okay, that is what I'm supposed to find. So if I'm just supposed to find that one, it should be like the distance traveled for 3 seconds minus the distance traveled up to 2 seconds. Okay, so if I'm going to subtract those two displacement, then I'll get the distance or displacement traveled in the nth second. Okay, so as if now you should be clear. Okay, so what I'm talking here, it is like displacement. Okay, so in order to get the distance traveled in the nth second or displacement traveled in the nth second, what I should do is I'll have to subtract the total displacement traveled in 3 seconds minus the displacement traveled in the first 2 seconds. Okay, if I do that one, that in between distance will be the distance traveled in that nth second. Okay, that is what I need to find, right? So this is something I've given it in numbers. Let's put everything in variables and get to know the answer. Okay, so here it will be something like this. In order to get the distance traveled in the nth second, it will be like distance traveled in n seconds, which means distance traveled in 3 seconds, total 3 seconds, minus distance traveled in n minus 1 seconds, which means s2. Okay, distance traveled in 2 seconds, right? Okay, it could be like if this was like 3, then it will be like 2. If this was like 4, then this will be like 3. Okay, so it changes depending on the time that you are about to choose. If it was like third second, then it will be like 3 minus 2. Okay, 3 seconds minus 2 seconds. If it was like 4, then it will be like 4 minus 3. That's how it's going to be. Okay, so now let's put like the kinematic equation that we have studied. So if I put that kinematic equation, in the first case it will be for Sn, it will be like ut plus half at square. That's what I used to substitute, right? So for u, that's going to be the initial velocity, therefore u. T, here t in the situation represents, this is like Sn, therefore t is nothing but the n seconds. Okay, so I'll substitute n straight away. If it was like 3, I'll put 3. If it was like 4, I put 4, right? So I'll substitute the n straight away as n. Okay, instead of t, I put n plus half at square, right? So here g should be represented with negative sign. Okay, so whenever I put like g, it actually means the object is falling downwards, right? So this is like a vector stuff that we'll do in the next chapter clearly. Okay, so you'll have to put directions into it. Obviously the ball is falling downwards, so downward should be represented by a negative sign, therefore I'll put that negative into the equation straight away. So you'll have like minus half g. Okay, it should actually be plus because of this acceleration due to gravity. I put that negative in front. Okay, I just multiplied positive and then negative. Okay, minus g t square. Here t square is nothing but the n square. Okay, so now I have got the first term. The second term, how should it actually be? So second term should be like negative of. You'll get the rest of the things, right? So the rest of the things will be u. Okay, instead of n, it will be like n minus 1 and then minus half. Okay, g n minus 1 the whole square. This is what you'll get, right? So next, let us do the inner multiplication and then I'll just expand it. You'll get the answer straight away. Just do the cancelling stuff, you'll get the answer, right? So if I do the inner multiplication, you'll have, first let me write the first term, which will be like un minus half gn square, right? So next, let us do the inner multiplication. First, you'll have this negative term, right? So when this negative gets multiplied to the first term, you'll have like minus un. Okay, minus un. Then you'll have like plus u, right? So you'll have like plus u. Okay, so the first term is done. Then for the second term, negative negative it becomes positive, right? So you'll have like plus half g n minus 1 the whole square, right? So in order to get that n minus 1 the whole square, you'll have n square plus 1 square, okay? N square plus 1 square minus 2ab, right? So you'll have like minus 2ab will be like n, okay? So now I have just got the entire term. Next, I will do the inner multiplication of this part alone, okay? So if I do the inner multiplication, what will I get? So let's put it this way. I'll just consider this term and I'll do the inner multiplication. So when I do the inner multiplication, you'll have the first term to be like half. It's going to be positive obviously. So plus half g n square, okay? So the next term will be like plus half g, okay? So the next term will be like minus 2 will get cancelled and then you'll have like minus ng, okay? Got it? Now let's cancel it out. So what are all the same things that are there? So you have something like this plus un and then you got like minus un. Those two things will get cancelled out obviously. Then you have minus half gn square and then plus half gn square. Those two things will get cancelled out. Then you are just left with u half g minus ng. So that's the term that is left, right? So let's write the final equation. So distance traveled in the nth second will be equal to u. Okay, that thing is done. Then like half g is common in both those things, right? So I'll just factor out half. So I'll have plus half g that is factored out. Okay, so the only thing that will be left inside is minus 2n plus 1, right? So either you could write minus 2n plus 1 or I'll just factor out negative sign from it, okay? So minus, I'll just factor out minus half, okay? So when I factor out minus half, this term, the second term becomes positive, right? So for a fancier equation, I'm just doing it, right? You should be able to understand this one. So I'll have something like this 2n minus 1, right? Got it? I'll just verify it for you. If you have like minus half g, if I do the inner multiplication, what will I get? I'll get like minus ng, right? So you got like minus ng. Same way if I do the inner multiplication, I'll get like plus half g. That's what I've written here, okay? So I just purposefully put it negative so that I get like 2n minus 1, right? Or else I would have got like 1 minus 2n, right? This thing seems to be fancier, that's why. So this is one of the formulas that you need to memorize, right? So generally I don't give you much formulas to memorize, but this stuff is in examination. If they give you this question, it becomes hard to do the derivation part, okay? If you know this one straight away, we will be able to solve the question, right? So that's the only reason I have given you this extra formula that you should memorize it, okay? So distance traveled in the nth second, right? So distance traveled in the nth second actually means in that particular second, what was the distance traveled, right? That is what we are finding here. So in order to get that one, I just used it like Sn minus Sn minus 1, right? And then just substituted S equals ut plus half at square and then I got this answer, right? So when you use this formula straight away, you shouldn't put negative sign. For gravity, don't use negative sign, okay? The reason is I have already used in the equation. So when I am about to generate this equation, I already used this negative sign in the main equation itself, okay? Therefore I'll just have to substitute 9.8 or 10. I shouldn't put minus 9.8 and make it positive, right? You will end up getting wrong answer, fine? So this one formula is something that you need to memorize extra because in the examination you could solve quick, that's why, fine? So now we are into the last part of this section, which is like relative velocity. Next one is relative velocity. Fine. So relative velocity always comes into picture when both the objects are moving, right? So when both the objects are moving, we'll be able to find what is that in between velocity, okay? That's called as relative velocity that we'll find here, okay? So here I have considered two person, okay? Person B and then the person A, right? So let's make it this way. Person B is actually moving forward with a velocity of 3 meter per second, okay? In this situation, the guy who is standing behind, okay, person A is chasing him with a velocity of 4 meter per second, okay. Let's make this situation simple. Obviously, it is pretty clear the guy who is standing back will be able to catch this man, okay. He will be able to catch the person B because he is having he is having more velocity when compared to the guy who is running forward. Okay, so he will be able to catch this person. So what is that extra velocity that he is having in the situation? That's called as relative velocity. Okay, so let's make it this way. Both those person are traveling with the same speed. For example, if both the person are traveling with like 4 meter per second, same speed, then they will never meet each other, right? Obviously, because in between distance is going to be same at every instant of time, right? So here, if they need to meet, obviously one should have greater velocity. Here I have considered the person who is standing back to be having more velocity. Okay, right? So what I'm about to find here is velocity of A with respect to B. That is what I need to find here, right? So you could also make another one argument, which is like, if I consider this person B to be at rest, what should be the velocity of this guy who is running back? Okay, if I can, both of them are running, but I am just considering that the person B is at rest, then what should be the extra velocity with which the person A is chasing? It should be like 1 meter per second. That should be the extra velocity, right? If both were moving at 3 meter per second, they'll never catch each other, right? If I consider the first one to be rest, what is the extra velocity here? That's actually 1 meter per second. Okay, so that is what I'm about to find here. So velocity of A with respect to B, which means I am going to consider both of them are running, but still I'm going to consider the B to be at rest. Then what should be the extra velocity? That's called as relative velocity. Okay, so in this entire setup, even though the earth is revolving, the earth is considered to be at rest because both of them are rest with respect to the earth. Okay, so even though the earth is revolving, I shouldn't consider that velocity, because in this entire setup, if someone is standing at rest, I'll consider it to be at rest, okay, at the surface of the earth, right? So it should be clear. So here, velocity of A with respect to B means actually B seems to be at rest. Okay, I'll consider B at rest. Okay, so the formula that I'll be able to put here is actually vector VA minus vector VB, right? The difference between them will give me that relative extra velocity, right? So that extra velocity is called as relative velocity. Obviously, that will be equal to 1. Fine. So here if I do the math, I'll get something like this. 4 is the velocity of A. So 4 minus 3, which will be like 1 meter per second. So this is direction sensitive, right? You should be clear with this direction. Fine. I have put an arrow mark above here. So this thing just represents vector. Okay. We will do this one exhaustively in the next chapter. As if now, this is direction sensitive. That is what you need to know. In the case of ball dropping, I consider G to be negative, right? Because this is moving downwards. Same way here, I'll have to put the directions carefully. Only when you put the directions correctly, you'll get the correct answer, right? Or else you will end up adding or subtracting. You'll end up doing the other way around, okay? So here the extra velocity is actually 1 meter per second. So this guy is closing the first guy with an extra velocity of 1 meter per second, okay? You can call it that way. Or else, let's make it other way around. Let's consider that VA to be at rest. Then it seems that VB is closing VA with a negative speed of 1 meter per second. Okay, it seems to be that VB is traveling backwards with the speed of 1 meter per second. That should be the answer, right? So if I find out VBA, then how should I actually get it? It should be something like this. Vector VB minus vector VA, right? Therefore, when you do the math, you'll get 3 minus 4, right? 3 minus 4, which will give you like minus 1 meter per second, which means the person B is closing person A backwards with the speed of negative 1 meter per second, right? So both those things are the same 1 meter. Magnitude is just the same thing. Only the sign is changing. So sign is changing with respect to the person that I'm considering to be at rest. If I consider the one who is front to be at rest, then the guy who is standing on the back is actually chasing him. That's going to be like positive. If I consider the person who is standing in the back to be at rest, then the person at the front is actually running behind. Okay, it seems to be in that fashion, right? Okay, so this is what is meant by relative velocity. You could actually feel this one while sitting on a train. Okay, when you sit in a train and then you look at the train that is passing nearby, you will get confused, right? Which is moving front or which is moving back. You'll get a little bit confused when the train is about to start, when it is at the train station. Okay, if there is a nearby train that is also standing, when one of the trains starts moving, you will get a little bit confused, right? Whether the train that I'm sitting is actually moving or the nearby train is moving. You'll be able to feel that thing. while sitting in a train or while sitting in a car, when you look at the car that is passing nearby, you'll have that confusion, right? So we'll get used to it, right? As time passes, we'll get used to that one, right? So when you feel that force, you actually think that we are the one who is moving, right? If you don't feel that force, actually the nearby train is moving, right? So in all those situations, that relative velocity comes into picture, right? You could actually do the imagination and you'll be able to get this one. So whenever you see relative velocity term, the thing that should pop up in your mind actually is the difference in the velocity. That is what we are finding here. Okay, so the next I have given you one more condition. So here, same way, you have like two guys that is standing. Okay, so the one of the guy is actually moving forward with a speed of 4 meter per second. The other guy is also closing him with a speed of 3 meter per second. Okay, so both are moving towards each other, right? In this situation also, same way I'll find the velocity of A with respect to B, right? So velocity of A with respect to B here seems to be like VA minus VB, right? So VA is actually positive, that is right. Fine. Minus VB. So here VB is actually negative x-axis towards negative x-axis. Therefore, it should be like minus 3. Right. So when I do the math, I'll have like 7 meter per second, which means they are closing each other with the speed of 7 meter per second. So this guy is moving 4 meter forward in 1 second. Same way, this guy is also closing by 3 meter. So together you'll have like 7 meter per second, right? So whatever the condition here is, whenever you get a relative velocity, you put one of the person to be at rest. Okay, with respect to A means A will be at rest, with respect to B means B will be rest. Okay, so when you do the subtraction, you just make an equation straight away. Velocity of A with respect to B means BA minus VB. If it was like velocity of B with respect to A, then it should be like BB minus VA. Okay, so these are all the things that you need to know regarding relative velocity. Using this relative velocity concept, we will do different sums. While doing POQ, we'll get a clear understanding of this thing. Okay, how to use this logic into the sum is something that we will do it in the sum part. Okay, so as if now all the theory part gets completed, only part that is left is that extra math logic. Okay, which we will do next. Fine. Here I'll consider a graph for a quadratic equation y equals x square, right? So obviously if y equals x square, then it should obviously be open upwards, right? So it is open upwards, which is like y equals x square. So in this situation, what I need to find here is what will be the lowest point for this graph. What should be the lowest point? That is what I need to find here. Okay, so if you need to get the lowest point by looking at the graph, it becomes easier. But the point is, if they have given you like x square plus 2x and then plus 3x cube, whatever it is, if they have given you n number of variables into it, then it becomes hard to plot the graph and to get the lowest point, right? So in that situation, I'll use a trick, which is the lowest point, slope should actually be equal to 0, right? From the graph, it is pretty clear. At the lowest point, the slope should be equal to 0, fine. Same way, there will be like another one graph in which it will be the highest point, right? First we will see for the lowest point, then we will see how to relate between this lowest point and then the highest point, how to find that difference. In order to get the lowest point or the highest point, what I should do is I'll have to find a point whose slope is 0. When the slope of that particular point becomes 0, then it means it is actually going to change from one pattern to the next pattern. So in this situation, the slope was actually decreasing, then it started increasing. Okay, so here in the other graph, it is obviously going to be other way around. So now I am about to relate between these two graphs. Okay, for the first graph, it is pretty clear from the graph. I will get the lowest point for slope equals 0, right? So to get the slope to be 0, what should I do? So first I'll have to find an equation for the slope, right? If the equation is like y equals x square, then in order to get the slope, what will I actually do? I'll differentiate it, right? When I do the differentiation, I'll get the slope of that every particular point, right? Obviously. So you'll have like dy by dx, which is equal to 2x, right? So now I have gotten variable term which gives me slope of that every particular point, which means the tangent of the slope, which means the slope of that tangent and that particular point, right? Or else slope of that particular point, right? So now I have got 2x, right? So here, when slope is equal to 0, what should be the point? That's what I need to find. So I'll equate this 2x to 0 and I'll get the x out of it. Fine. So next what I'm about to do is, whenever they give you an equation and they're asking you to find the highest or lowest point, what you should do is you'll have to differentiate it and then you'll have to equate it to 0, because when the slope becomes 0, then it should be either lowest point or highest point. With that trick, I'm going to do it. Okay. So here I'll equate it just with 0. So 2x will be equal to 0, right? If you get n number of other terms, you'll have like multiple terms into it. It will not always be equal to 0, right? So in this situation, x will be equal to 0, fine. It could be some other point. If this x square plus 2x cube, if you get some other equations into it, okay? Some other variables into it. So here 2x equals 0, which means x is equal to 0, right? Now I have got like x is equal to 0. X is found. So in order to get the other y, what I should do? I should substitute this x is equal to 0 in the parent equation, okay? So in the main equation, if I substitute it, I'll get y which is also equal to 0, right? So now I have got a point. The point is actually 0 comma 0. So 0 comma 0 should be the lowest point or the highest point. In this situation, it is obviously the lowest point, right? So in order to get the highest point, in order to verify it, whether it is lowest point or highest point, what I should do is I'll have to differentiate it one more time. So I'll differentiate this equation one more time, which will give me like d square y divided by dx square. I'm going to differentiate it one more time. If the answer is like positive, then it is lowest point, okay? So if the answer is positive, then obviously this is going to be lowest point, okay? So this is called as local minimum, okay, or minimum point. Same way, if I have to find the highest point, what should it be? It should be the same pattern. I'm going to do the same stuff again, but the thing is, the double differentiation of the equation will be like negative, okay? So whenever you have the double differentiation to be positive, then actually the point that I have found is lowest, okay? If the double differentiation is going to be negative, then the point that I found is actually highest, okay? So it should be like other way around. Let's verify it. Got it? So here I have taken y equals negative x square, which means this is like open downwards. Obviously in this situation I need to find the highest point, okay? So first I'll have to find like slope, which should be equal to 0. Then from that point, if I do the double differentiation, then I should get that answer to be like negative. Let's verify it. So here you have y equals minus x square, right? If I differentiate it once, I'll have like dy by dx, which is equal to negative 2x, okay? Then what I'm about to do is I'll just equate it to 0, fine. So if I equate this one to 0, you'll have negative 2x, which is equal to 0, which means x will be equal to 0. Now I have found x value of x. If I substitute this x, okay, into the parent equation, I'll get again 0. So the local minimum or local maximum point is obviously 0 comma 0, right? From the graph, it is pretty clear. It should be like 0 comma 0. That part is done. Next, what I'm about to do is I'm just going to verify it once again with the double differentiation. When I do the double differentiation, you'll have d square y divided by dx square, which is equal to minus 2x. If I differentiate it once, I'll get like negative 2, right? So here the value is actually negative. Got it? When the value is negative, it is pretty clear that the point that I have found here is actually the highest point, which means local maximum, right? So you should be clear with this extra one math logic, okay? So it will be helpful and handy in the upcoming chapter also. We'll solve one or two sums related to this logic also, okay? So you should be clear with this one, right? If they're asking you to find the highest or lowest value, it could be like highest velocity or the highest acceleration, whatever they give you. What you do is you just take the equation that they've given and then do a differentiation, equate it to 0. You get either highest or lowest velocity, okay, with respect to the time. And then in order to verify whether it is highest or lowest, what you should do is you'll have to do the double differentiation. Got it? When you do the double differentiation, if the answer is like positive, then it is actually lowest point. If the answer is like negative, then actually it is like highest point, okay? So these are the things that you need to know in this chapter, right? So this part might be exhaustive and a little bit lengthy. So the thing that we have studied in this part were like graphs between acceleration, displacement, and then the velocity, okay? Then we did see those kinematic equations, fine. So we did see all those kinematic stuff, equation stuff. Then finally we saw like relative velocity, okay? So those were the things that we saw with some extra math logics into it, okay? There shouldn't be any doubt in this part. With this, the video gets completed. Bye.